Okay, let's try a few more conceptual problems here. Question 4. You are sailing a boat in the fresh water of the Columbia River and decide to take it out in the open ocean. As you transition from the fresh water to the salt water, which of the following statements is true? Will the boat float higher in the ocean than it was in the river, or does the boat float higher in the river than the ocean? Well, let's try drawing a free body diagram. Let's remember that there is a buoyant force going up that should be equal and opposite to the weight of the boat if you're floating in equilibrium. Remember, Archimedes' principle says that the buoyant force is equal to the weight of the fluid displaced by the object in the water. That's going to equal to the mass of the fluid displaced times gravity, which is going to equal the density of the fluid displaced times the volume of the fluid displaced times gravity. If you have a bigger density, that means you don't need as much volume in order to be displaced in order to create the buoyant force. So, in other words, the boat is going to float higher in the river, higher in the ocean than in the river. Actually, several hundred years ago, before we knew how to do everything we know how to do now, the way you would determine if a boat was going to float or not is you would make the boat, try it out, and if it didn't float, well, you wouldn't do that design again. And for several centuries, we have records of people in Europe trying to make boats that could work both in the river and the ocean. They'd make a boat in the river, they would then float it out to the ocean, and of course it would go too high and tip on over. Or maybe they'd go the other way, they'd make the boat in the ocean, try to bring it into the river, and it would sink. And they'd try it again and again, and just never could they figure out how to make such a boat. One of the reasons why the British were able to take over the planet is they learned how to make boats that would work both in oceans and rivers, and that allowed them to get past the coastal defenses in China and go inland on the rivers and take over that country of, now 1 billion people. Not quite so many people back then. Okay, question 5A and B. Which best describes the principle that allows an airplane to fly? Well, it is the shape of the wings that cause air to go over the wing at a higher speed than under the wing. That makes a low pressure patch over the wings, and then your airplane flies. That's called Bernoulli's principle. Meanwhile, a hot air balloon floats or flies because it uses less dense air to displace higher density air. And of course, we know that is Archimedes' principle that says the upward buoyant force is equal to the weight of the displaced fluid. Question 6. Here we see a snapshot graph and a history graph of a wave pulse on a stretched string. These two graphs describe the same wave from two different perspectives. In which direction is the wave traveling, and how fast is it moving? Okay, let me see if I can blow up this picture just a little bit. I don't know how well you can see it back there at home. So we have in the left picture, we have the snapshot graph at t equals 0.01 seconds. And in the right picture, we have a history graph of what's happening at x equals 2 centimeters. So notice that t equals 0.01. Currently, the entire wave is hanging out in the negative part of the x-axis. We are seeing the history of what's happening to an object at x equals positive 2. If the wave was traveling to the left, then it would never ever get to positive 2. So that means that this wave must indeed be traveling to the right. So the velocity is to the right. The next question is how fast is it going? Well, notice that the first part of the wave at, so this part of the wave right here at t equals 0.01 seconds, one side of the wave is at x equals minus 2 centimeters. It's moving to the right, and we see that this part of the wave finally gets recorded at t equals 0.3 seconds. Where are we going with that? Oh, okay, so the wave point at t equals 0.01 seconds at x equals minus 2 centimeters ends up at x equals plus 2 centimeters at t equals 0.03 seconds. Remember that speed is change in distance over change in time. We're going 4 centimeters in 0.02 seconds, and that means that our velocity is going to be, let's see if we can divide by 2. I'm sorry, it's very late here, guys. That would make it 400 centimeters divided by 2 seconds equals 200 centimeters per second, which is, of course, 2 meters per second. So the answer should be 2 meters per second. Okay, I think that's going to wrap it up for now. Do well, everyone, tomorrow on the test, and I look forward to seeing you in lab on Thursday. Good night.